Hello, folks. Welcome to Rational Science. And today's what? The 21st of December. We start winter over here where I'm at. And now is the winter of our discontent. So said Shakespeare. Anyways, we have a great day today. We're going to be answering some questions first. A couple of people asked important questions. And I'm going to answer those first. Then I'm going to move into the main course. Okay, so let's get started here. First with the questions. And I hope everybody is seeing me. Seem to have an issue here. Oh, okay. Anyways, sorry about that. Fellow asked the following question. He said, please address the issue where they claim to collide atoms inside particle accelerators, right? And form new, heavier atoms that are very unstable and only last a few milliseconds. What are they actually detecting there? New, heavier atoms? And I think it's an important question. What are they doing at these accelerators? Are they making new elements? And if so, for what? I mean, what's the purpose of it? A lot of these elements, according to them, right, last very few seconds or milliseconds, and so it's just, oh, we saw it. Great, there it goes. Here it comes, there it goes. It's like, so I don't know. I don't know if it's worth it. But yeah, let's answer his question. Here's the periodic table. Okay, and you see all those elements there, and they're all different. And the question is whether they were always there. Can they be manufactured? Can we make the ones that are heavier elements, which are the ones at the bottom, right? Is that possible? And that one thing is for us humans to make them. The question is whether they're made naturally, by Father Universe up there somehow, and obviously the story is that, all these elements, higher level elements, the heavier ones, are made from collisions inside the stars of protons and whatever, atoms, etc., So the issue is, that is the official story. But there is an earlier story to that. In other words, in the progression, the chronology, they say these elements were made right after the Big Bang. And here's the history of the universe according to NASA. And you can see circled in red the first particles, the first nuclei, and the first light. So there was no light until, what was it, 380,000 years after the Big Bang. And of course, the question they never answer is what happened there at the Big Bang itself, 13.8 or whatever, 14 billion years ago, rounding off. And, how did we get that something out of nothing? That's the issue. You have Larry Krauss, he says, something out of nothing. Yeah, I want to see that. Now, don't tell me it happened. Tell me the mechanism, okay? And so, we have this situation where you have the universal movie, our tool. And they say that God created the singularity in frame number 2. It's already there. So the question is, what happened in frame number 1? How did we get from frame number 1 to frame number 2, from nothing to something? That's the only one they have to explain. And that's the one they say, well, it's an unscientific question. We don't do that kind of work. We do math, and we can tell you that it all started, blah, blah, blah. Description. They cannot tell you an explanation of how something came from nothing. Period. We're done. But that doesn't rule out that we can make higher level elements, higher masses, etc., elements from lower masses, right? From smaller atoms. Like, can you take hydrogen, bunch of hydrogens, and somehow build up all the way to uranium or whatever. And this is the version that they have. This is the what they think is happening inside the sun. So let's zoom in into the sun. Let's find out what's going on in there. Here we have it rotating, okay? And what we're going to try to do is zoom in there, okay? See what's going on inside that sun, right? All those particles that we will be seeing in there, and this is how they illustrate this, okay? Here it is. The one on the left is their version. The one on the right is going to be our version. We have the quantum version collisions. That's what they think is happening. We're saying that whatever happens in there, it's not a collision. There is no motion inside the center of the sun because everything is being squashed by gravity. Remember? I mean, these people have all these particles, especially protons, running around, moving at great speeds inside there. I thought the sun, like all stars, are gravitationally collapses. And if it gravitationally collapses, I hate to be in the center there because, all those particles are being pulled from the other side of the sun, and the particles over here are pulled from the other side of the sun. The ones from north are pulled from the south from the north. And guess what? In the center, it's all squashed. So you cannot have really all these particles traveling at the speed of light, as they say, in the center of the sun. So there are no collisions inside the sun. We can produce collisions here at the accelerator. That's what those are doing. They're accelerating these particles, right? Colliding them. But is that what's happening inside the sun? Is that how we make higher level elements? And the question I'm saying is, no, that's not the way they make them, the way the sun makes them, And so we have a difference. Here's the official version again. You go inside the sun, okay? And you can see the particles, they're moving at great speeds. And so they're saying there's a lot of empty space in there for these things to move around. You can see they're all moving at great speeds and colliding against each other. And so the question is whether that is exactly what's happening inside the sun. And what we have a different version, and here it is. We have gravitational collapse pressing into the sun, okay? All the atoms, remember the atoms are made out of threads that are wound around, so they're physical. The electron is a physical surface, not a little bead. And so you can see how it's squashing the atoms together, and that's how it builds higher level elements. Okay, that's our version of how higher elements are made. Okay, they're just squashed in there by compression, and it should be like that because it's a gravitational collapse. And so they never were able to reconcile, the gravitational collapse with the movement, the extra movement, the degrees of freedom they call them, all that movement that the particles have in there. It shouldn't have any movement in there, or very little, if anything. It's really compressed, and that's the only difference. But other than that, we agree with the official version that heavier elements are made from lighter elements. So from hydrogen, you can make helium. From helium, you can make, lithium, and so on down the line. So we think that's the way it's done, and we think it's done inside the sun. As I understand it, was Hans Bethe who came with that theory. So we got to take off our hats to him. He was a mathematician, but that one he got right. That one he did physics a little bit, okay? Okay, and one of the issues is how does the light get out, and also electrons come out, and one of the subjects we have today is that, the fact that you have this decay and the electron comes out, and you have also the positrons and all this stuff. How do they come out of the sun if everything's being squashed inwards? You're talking about matter here, supposedly. I mean, I think an electron is considered matter, but we don't know because quantum is, they never specify anything. But if an electron is a physical object, and the positron is a physical object, a little ball of some kind of little bead, how does it get out? How does it get out and reach, this remember there's a solar wind made out of electrons and other garbage. And so the question, how does all that stuff get out of the center? And they never explain that. They just says it does. Again, they have this mean-free path through which these tunnels, I guess, where the electron can get out. But they never explain how. if everything's being compressed. And again, we have a contradiction there in logic, right? There's no logic to what they say. And so our version is, here's our atom, it's pumping back and forth. Okay, that's your quantum jump. And by doing so, it torques the rope, and that's light. We're done. That's how simple our universe is. That's the basic system, right? And as far as getting out, the energy getting out, well, this is how it's done. We're saying that the atom is pumping back and forth. And we have that at the surface of the electron shell. You have a little bit of friction between, the ropes and the surface of the atom. Okay, that's what we're seeing there. And so that's the aggregate of all those of all that pumping at every location around the atom. That's what we call energy. Okay, so we have a way of getting the energy, so-called energy, right, out, and we can explain charge physically, unlike them, that they just have a number for charge. And so the question is, how do they explain this? How do they explain that the energy gets out of the sun? And, you have to keep in mind what they do. They cheat a little bit because they talk about mass and energy. Mass supposedly is particle, thing, and energy is an abstract concept. Whatever it is, they never defined it and say they don't know what it is, and they just leave it at that. And so they never specify it, so you can't get a physical interpretation. So what happens? They turn mass into energy. And so you say, well, did the mass come out? Did the electron ball come out? And they say, no, the energy came out. Oh, what is the energy? What thing is the energy that's coming out? And they just give you a number. They say it's a value. And that's it. That doesn't get any better than that. So yeah, we have an explanation for how the sun compresses atoms and builds higher level atoms. We agree with that version, but where we disagree is on two counts, and those are both related to gravitational collapse. On the side of the center of the sun, we don't have any room for the particles to be moving and colliding like they say they do. And on the coming out, the energy coming out, again, they never explain how it goes against the gravitational collapse, how the particles, whatever particles, electrons, positron, whatever they want to put in there, I don't care. How does that particle get out if there's all this compression going towards the center? And that's the question you should ask. Okay. Okay, another question that someone popped up, but really, an issue that was brought up, and I think it should be addressed. And it's this one about, essentially, what is physics? What is physics? I mean, what do we do? Do we do math in physics? Do we do experiments in physics? I mean, what is physics about? And here's the question. It says, physics draws relationships, builds descriptions, and makes predictions. This is his version. It works operationally, whatever that is, and remains largely indifferent to ontology. In other words, it's a practical discipline, a pragmatic one. You use your hands, your eyes, you don't use your brain. Okay? Questions about what things actually are, what exists, and what mechanisms underlie observed regularities belong to natural philosophy, whatever that is. Okay? And more fundamentally to metaphysics, whatever that is. So we have natural philosophy and metaphysics. Jesus Christ, what is that? Modern physics doesn't care about what you want physics to be. It's just math. Okay, so this is the version that a lot of people believe in this. This is the one they subscribe to. And so, we have a problem because all these people, they keep bringing this up every time we talk with them, And so, yeah, what can I say? These people actually believe all this stuff. Oh, hold on, got something here. And this is what they teach. This is what they learn. This is what is propagated from generation to generation, or like I like to say, from generation to degeneration. Okay. Anyways, here's an answer to that. The answer is, physics is not really about running experiments or even taking measurements or doing math. None of that is physics. Physics is about explaining, and math cannot explain. We're done. That's where the whole thing stops. Uh, Physics explains, and math only describes. So math can never be part of physics or of science for that matter, because science is also about explanations. And experiments, you can experiment with what you can see and touch. That's why you go to the lab or to the field. You know, you're going to use your eyes and you're going to use your hands. And that's not what we do in physics. We don't do that at all. We don't do experiments. We do not take any measurements. We do not calculate anything. We do not describe. What we do, we have to explain. You can do whatever experiment you want at home. You can do the calculations you want at home. It doesn't matter. When you come to the conference, you have to explain, okay? Don't do an experiment for us. Don't tell us what you measured. Don't tell us that you measured more accurately than the other guy. You know, we don't care about any of that. You come to the conference, you have to explain what you learned or what your theory is. That's what physics is about. Physics is about theory, and theory is only about explanations. It's got nothing to do with descriptions. And so that's where we have a problem. And this is where this fellow comes in. He says, well, that's what they do. We don't care if that's what they do. Not because it's something is broken and we have to fix it. We can't say, let's continue doing it like that, because that's the way the mathematicians do. They call themselves the physicists, and that's what physics is in reality. We don't care about any of that. We wipe it all aside. We don't care. That's mathematics. They want to do it over there. That's fine. In Cambridge, Harvard, we don't care. We're saying that there's something wrong, and the reason there's something wrong, we have no answers. We don't have the answers to our question. We have no idea what this universe is, how it works. We have no idea of anything. And we're going to see a little bit of that today. But here it is. Here's a rundown, essentially, our position. Math is not the language of physics, okay? In physics, we don't, this is the language of mathematics, okay, that you're seeing here. They carry a force, bend time, transfer energy, pull with particles. That's what they do. Move up mass, and they warp space-time. They observe a particle at two places at once, you know. Magically make a particle appear and then disappear, known as virtual particles. They trigger action at a distance with nothing in between, right? No mediator. They travel faster than light, despite that there's a contradiction between the quantum faster than light and the version that special relativity has, which is that you can only travel, that the maximum speed limit of the universe is the speed of light. If it weren't like that, there would be a serious problem with all of special relativity. We would have to trash it. Now go ask the mathematical physicists to trash special relativity, and I'll tell you what they'll tell you. So we have a contradiction between special relativity and quantum mechanics, and nobody's resolving it. They just leave it at that. You study special relativity when you go to special relativity class, and you study faster than light when you go to quantum, and everything's okay and dandy. Nobody reconciles any of that. And then they talk about squeezing through wormholes, right? So all this irrational jargon that is the language of mathematics, this is not the language of physics. Okay, so let's get that straight at least. So if this is the language of mathematics, it has nothing to do with physics. We do not have that language, that jargon in science. It's an irrational language altogether. And here's the other part of that, okay, the other argument. Theory is not mathematical description. Theory is what? Explanation. We want a mechanism, we want causes. People want to know why a pencil falls to the floor. That's the question they're asking, and these people cannot answer that question, that simple, very simple question, in the last 10,000 years. Not one researcher has been able to answer that. Language as physics is illustration. Why? Because physics is done with objects. You cannot do physics without objects. You had better have an object out there in the universe, anywhere in the universe, if you're going to do physics. Otherwise, what's happening? If there are no objects, what would be happening? And so these people want to do physics without objects. What they do is they try to explain mechanisms by moving concepts, okay? And so they have this notion that an object is that which you can see, you can touch, maybe it's what has mass, maybe volume, maybe that is which is made of matter. They have all these definitions, these notions in the back of their mind, and they never thought that there are objects out there that you cannot see or touch. That's why when they have entanglement or they have gravity, they cannot understand it because they can't see the pull. They know these are pull or contact forces somehow, but they don't have a mediator. They say, well, we can't see anything in there, so there's nothing there. But that's because they have this notion of the see and touch version of object, of what a thing is, what a mediator is. And no, an object is that which has shape, and it's not that which you can see or touch. And the following words, that you see there of mathematics are not objects. Field, energy, mass, time, momentum, wave, none of those words, none of those terms that you see there represent objects. Not one of them is an object for the purposes of physics, okay? And so what happens with all these people? What happens? These people today cannot explain anything. And the question is whether their job is to explain. If it's not, well, I don't know what physics is, because I want to know why the spoon falls downwards. That's what I want to know. If this is not a question of physics, what is? I mean, what are we going to say? That this is a question of philosophy, of ontology, of metaphysics, natural philosophy, as he said? Is this falling of this? It's not a question of physics. This is not physics. And so this is what blows my mind, that all these people have something very straightforward and they're turning their heads, say, that's not physics. Okay, so what can I say? Shoot myself. Okay, so we have all these people, and here there was a fellow who sent me to a video. I don't know if this is the right video that he sent me to, okay? But it was the one I found out there. And so here it is. Let me show you. This is the video I think he was talking about, maybe. Okay, anyways, at least one guy sent me to this and says why particles might not exist. And so now they're debating. This came out a couple of days ago, so this is fresh, right? And they're talking about, whether in quantum mechanics, whether they're going to deal with particles anymore or not. And here you have Sabine Hassenfelder and a couple other guys. One of them is Tim Walden. The other one's Hillary Lawson. They're so-called philosophers of physics, philosophers of science, whatever that is. We don't know what that is. In science, there's only physics and philosophy. That's it. Those are the only two branches of science. Okay, there are no other branches in science. And then under that, there is no such thing as philosophy of science, philosophy of physics. Now, the philosophy, so-called philosophy, the metaphysics, the ontologists, all these people, I don't know what they're doing. We did not need to break up every word into a different category and create all these different branches of so-called physics or philosophy or whatever they call it. No, there's only physics and philosophy. Physics deals with the inanimate world, how things move, okay, in the universe, including here on Earth. And then philosophy deals with behavior, okay? Philosophy has to do why someone did something. Okay? Why did Caesar go to, England? What was going through his mind? Or why did Joe rob a store or kill his wife or whatever? Those are questions of philosophy, okay? The whys. So those are for psychiatrists, historians, anthropologists, people like that. Physics deals with inanimate matter, how things move in the universe on their own or however. We need to study that and understand that. And that's what these people don't do. And so today, none of them can answer the questions. And so here's how they started their debate. All these three stooges went out in circles. And here, I want you to listen to them because it's so funny that they cannot answer simple questions. And like, what is a particle? What is a field? Is a particle the same thing as a field? Is a field the same thing as a particle? And if it's a particle, what is a particle? What is a field? And so this is the type of question they're going to try to answer, but they go around in circles because they're stooges. That's what they are. Here, listen to them.
The particle is just a vibration in the field. We don't have to postulate a metaphysical other thing.
No serious physicist. I don't think there's any serious physical theory that says that. People speak loosely that way, but it doesn't make any sense. So you can't think of particles as fluctuations of fields if the fields aren't in space-time.
There's fields and particles as a separate sort of structure.
Sure. There are always different ways to look at the same thing. So it doesn't really make sense to say the particle is the thing that is real if there's another description that's exactly as good but doesn't have the particle.
Okay, so they go back and forth for particles and fields. What is a particle? What is a field? You know, and they have these arguments where they go around in circles. Why? Because they never define what a field is. They don't know what a particle is. They have different notions of particle. It's the waving of the field or whatever. And the worst part is they seek evidence of a particle. It's like, you know, please define what a particle is. No, we look for evidence of a particle. That's the way they look at it. And here, listen to good old Sabine. This is how she presents her case. She's going to look for evidence of particles. Okay, here it is.
We call a thing a particle if we have evidence for it, and we have mathematics to explain this evidence, and then we can define something that we say, well, this is a particle. The stuff that is a particle for us in the laboratory is no longer a particle in this other description, which is mathematically exactly as valid. So it doesn't really make sense to say the particle is the thing that is real if there's another description that's exactly as good but doesn't have the particles.
So they're looking for evidence, and they say, well, this one we'll call a particle because we were able to sense it somehow, and they say that's a particle. What do you, I mean, they think it's through see and touch, and they say we touch something, so it's got to be a particle. So what is a particle? I mean, is it a discrete entity? Is it a ball? What are we talking about? You know, and they just use the word particle very generically, and then they tell it's a vibration of a field, and a field, what is field? A bunch of numbers. So they're vibrating numbers, and they call that a particle. So this is where the problem is. We have a serious problem because none of that has anything to do with physics, philosophy, or whatever. This is just irrationality to the 40th power. And here, Tim Malden also will tell you that he's looking for evidence. Everybody looks for evidence, you know, talks about evidence.
Some articulated theories postulate their particles, some postulate their fields, some postulate their strings. The question is, what kind of evidence could we have that might make one of these plausible? So you have to look at any of these theories, what's the evidence? And you're asking for definite reasons to believe them.
So what is evidence used for? For belief. It attacks belief. You have a different belief, I'm going to change it. And here's the evidence. That's the point of evidence. And these people are looking for evidence in order to change beliefs. They call it knowledge, but what it amounts to is belief. These people simply have beliefs, and they think that science is about belief. No, religion is about belief, not science. We don't look for evidence in science. What we need to do is sit back and think and try to visualize what Mother Nature, Father Universe, the devil, whoever's out there, you know, how they run their shop. That's the way it works. But to say that, you know, I'm going to look for evidence of a particle to change your beliefs, you know, I mean, is that science? Is that what science is about? And here, Tim Malden shows you how they determine what a particle is, why they have evidence of particles. Okay, listen to this one. This is a very important one. Okay, this is Tim Malden again. Okay, listen to him.
We have phenomena like little dots appearing on screens, and certainly one handy thing for explaining that phenomenon is to think there was a little invisible thing that pretty much hit the screen there.
So you're saying, what is he talking about? Well, if you recall in the slit experiment, you have these particles going through the slits, and they claim they were able to handle each particle individually, whether it's a photon or an electron. You know, they did it with electricity as well. They say they were able to handle one particle at a time and direct it towards the screen. This is their claim, okay? And here, you see this in the Dr. Quantum, okay? This is Dr. Quantum doing this. Here you go. Look at him. One particle at a time, okay? Goes through the slit, goes through two. It's at two places. That's the same particle, by the way. Okay, it's at two places at once, and then they converge and hit the screen. This is the mechanism they propose for how the slit experiment is done, okay? And so, yeah, the question is this the correct explanation for the slit experiment? It involves magic. They see the particle, the rabbit is at two places at once. Is this possible? Does this make sense? Is this logical? Okay, and so the answer is no. Mother Nature hopefully is a little more rational than they are, right? And here's one fellow who claims he handled one electron at a time. Also, according to Tim Maulding, they were able to handle one electron at a time, and therefore they know that an electron is a particle, a discrete little ball. That's what they say, okay? And so this is Tanamura, okay? And he did it at the right after a fellow by the name of Gerli in Italy. But see, they're saying they detected one particle at a time. And that's why they say you can be confident electrons are particles. Okay? And the question is this true? I mean, are electrons particles, like discrete little balls? I mean, I'm talking about this. Is that what an electron looks like? Because that's how they treat it in all their dissertations. And then when you put them against the wall and say, well, is the electron only a particle? And they say, well, no, that's, we don't know. And we don't know if it's made out of something smaller. They don't know anything about it. But they say they handled one electron at a time. Why? Because they saw a little dot on the screen, right? One dot next to the next dot, the next dot. They say, hey, we're handling one electron at a time. Look, I can prove it to you because I'm making, I'm shooting the bullet to the wall, and I'm making one notch here, another one there, one hole here, another hole there. So it's got to be a particle, right? A discrete little particle. That's how they determine it through experiments. So this is how they do it. Here you'll see more or less what they have through their minds, right? When it's going through their minds. Here it is. Guy shooting, right? And this is how they think it's done. And the question is this the correct interpretation, And we have a little different one. And here's the one we have coming up. And it's the drill bit. Okay, we drill holes. That's how we made those holes, not through bullets, but drilling. It never occurred to them that there's an elongated object going from their source to the screen. It never even crossed their minds that there could be, a connection between what you have and, a little drill that's got this drill bit going all the way to the wall. And it never occurred to them because they say, we don't see any drill bit. Well, yeah, because you cannot see or touch the mediators that Mother Nature uses. That's why. That's how simple it is. And Hillary, this other fellow, okay, he goes in there and he says, actually, there are no particles, okay? Listen to him.
When if you think of an electron, you probably have a picture of a sort of atom in the middle and the electrons somehow going around the outside. In field theory, we see that particle as a vibration in a field. We don't really think of it in terms of particles anymore. We think it in terms of fields. But it's a probability space in which there's no particle to be found anywhere at all. But what is that? What is that vibration in the force field, the electromagnetic force field? There isn't a single answer. The world isn't made of bits that might have answers like that. Interesting.
So they go back and forth between fields and particles and fields. They gotten away from particles because now it's called quantum field theory. No longer do you have the discrete entity that quantum started with. Now it's this elongated thing that stretches throughout the universe called the field. And locally you have an ocean, and locally you have a wave or a current, local current, and that's what they call a particle. That's what they're moving towards, because they can describe that mathematically, whether that's what's happening or not, right? And the other fellow, this Tim Malden, he answers again. They have no idea what a field is, and here it is, his answer.
Let's start with some definitions. A particle is always somewhere. A field is always everywhere. A field classically is postulated at every point in space and time it has a value. A particle is always somewhere, and typically what people mean by a particle is more than that its trajectory through space-time is continuous. You don't think of particles as discontinuously jumping around.
So I like the fact that they don't have a definition for the word particle. They just keep running around it in all sorts of, they're going to prove the particle, they're going to run an experiment on the particle, but they never define what a particle is. It's like, the NASA biologists, they're so smart, they're going to look for life on Mars. They never defined life. So how do they know if they found it? How do they know if they lost it? I'm going to find what I lost. What did you lose? I lost my life. What is your life? Oh, I don't know. I have no idea. So they're going to Mars to look for life, and they don't know what life is. They never defined the word life. And these people are in the same boat. They're saying, we're going to look for a particle. Why are you looking for a particle? What is a particle? Oh, we have no idea what a particle is, but we're going to look for it. Great. We detect it. We define it by detecting it. It's a, what is it? What they call one of those definitions. What is it? Operational definition. That's what it is. They define it by operating. Okay, that's how they do it. Anyways, you can see that the world of mathematical physics, what they call physics, is irrational. It starts at the base. They don't know what an object is, therefore they don't know what a particle is, but that's what they work with every day. Are they working with particles? Are they touching particles? No. What they're working is with math. They do an experiment. They see something visible, whatever's visible there, right? And whatever effect that causes, they call that a particle, a field, or whatever. And then they come back, do some more math, and they keep going around and around and around, and they cannot explain to us anything about the universe. Absolutely nothing. They cannot explain electricity, magnetism, gravity, nothing, none of that can they explain. And so we have a problem, because these people can, what's the point of having them if we're paying all these big bucks to have these people at colleges and at think tanks, and they cannot explain something as simple as, again, why this spoon falls downwards. They cannot explain that. And obviously they cannot explain this other one either. They cannot explain how this magnet attracts that one, what the mechanism is, how Mother Nature does this. It's a field. Well, yeah, you haven't told me anything by saying it's the field. What is a field? Well, as you can see, they have no idea what a field is. It's a bunch of numbers. It's just stuff they measured at a certain region. They say we measured. We have numbers. We have values. That's what a field is. It's defined as a value at each point in space. That's not a physical object that you could say that's what caused, right, one magnet to be attracted to another. And same with the gravitational field. You haven't explained what the mechanism. That's what they're still looking for gravity to this day, because they talk about the gravitational field, but they don't have a mechanism. They say we don't have any meaning. We can't find any meaning in any of this. Yeah, no kidding. It doesn't surprise me. Okay, another fellow, he asked me to look at a video. Again, I have no idea what video he was referring to. But I took the last one that came out from this fellow. His name is Muller. And he says, new Mr. Derek Muller, video out, Bill. Would love to see your breakdown on it. Okay, so what did this fellow talk about? Well, as you can see there, he says that he lives in many worlds. I live in only one, but he lives in many worlds. Okay, is that possible? What kind of nonsense does this fellow have in his head? What was he taught? And then you can see the red arrow goes faster than the blue one. The blue one supposedly is the photon. The other one is, I guess, a tachyon, whatever. So why did they raise these issues? Well, because again, what happened was that special relativity said that the speed limit is of the universe, right, is light, 300,000 kilometers per second. We're done, right? And that's been proven, certified. Einstein said it, so it's like it came from God, right? Einstein said it. We're done. No more needs to be discussed. And so what's the issue? Today they say, well, what if we could travel faster than light? What do you mean? We've already settled that. You can't. If you want to do faster than light, you got to go outside of science. You can do some fantasy out there, some science fiction, sell your book to Hollywood or whatever. No problem. But don't bring it into science, because these guys have already determined the maximum speed of light is 300,000 kilometers per second, which is the speed of light. Don't change that. But they have changed it. They've gone overboard, and it's like, they teach both. You go to college, you go to the class, special relativity class, they say, speed limit, light. Okay, we're done. Then you go to the other class, to the quantum class, hey, we have something faster than light. And they live with both these contradictions. They never resolve them. They call them dualities. They love dualities because it allows them to, skirt any control. What's the point of all that if they're going to have these different opinions of how the universe works, right? And so here's the again what Derek Muller was trying to explain was EPR. That's got them going crazy. They say you can't have instantaneous connection, instantaneous communication, instantaneous transfer of information, whatever that is. In physics, we don't transfer information. That's nonsense that the mathematicians invent and talk about. Transferring information. I can't transfer information because information's a concept. It's like saying I'm going to transfer love to you so that you can love me. Great. I wish I could do that with some girls out there, but it doesn't work. I can't transfer love, and I can't transfer information in the same way. You can transfer a cow, you can transfer a rock, you can transfer a house, a tree. You can't transfer concepts. And these people are transferring concepts. They call it information. And so the question is, you have two balls, right, for the EPR entanglement, okay? And this one does something, and it affects that one with nothing in between. And so the question is that science or is that black magic? I mean, what are we talking about? How can this particle affect that one in any way, shape, or form, and without a mediator? And so in physics, we need objects. We can't do physics without objects. And these people are doing physics without objects. They had to explain how this particle that's on the other side of the universe affects this one over here. And you say, well, obviously, we don't call it black magic. We call it faster than light. But then they had a problem with that. And they said, no, if you have faster than light, that violates special relativity. And so we get into all these contradictions. And so they solved the problem of these Derek's proposing that what's really happening is there are many worlds. Okay, that's why he lives in many worlds at the same time. So he lives in all these worlds, and he says, in this world this happened, in the other one something else happened. Or, this world affected that world, but they exist simultaneously. So that's the solution they give, even though it's totally irrational and nonsense that should never have entered the world of science, the world of physics. That is one of the important explanations they have today. And so this is his ending. I didn't want to go through his whole video analyzing each point that he made. It was all trash because he was talking about particles, and that's where it all goes to hell. You can't explain things such as gravity or entanglement with discrete little balls, which is the notion people have in their minds when they talk about particles. There's nothing flowing because that's what they're talking about. They're saying this particle sends something to the other particle faster than light. That's the notion. So that there is a mediator, which is this little particle, right? They can't see it, they can't touch it, but that's the only way they explain it. But then if you're doing gravity, how do you pull by sending a little particle? You can't not explain it. And the same thing more or less with entanglement. But here, listen to his bottom line. He says that EPR and entanglement, we don't need to explain it with faster than light. we can explain it with many worlds. Okay, listen to him.
This is what the many worlds interpretation of quantum mechanics proposes. When you measure a particle, instead of you collapsing the particle to one outcome, both outcomes happen, and there's two parallel versions of you who sees each outcome. You have become entangled with your particle because your state depends on what the particle is doing. It sounds strange, but there's one huge benefit of this interpretation. When your friend is about to measure her electron, your positron doesn't need to rush to tell the electron what the answer will be. There are already two versions of the electron, and they contain the right answer for each version of her. There was no need for faster-than-light communication to explain the EPR experiment.
See how easy it is to explain stuff in mathematical physics? Because they don't define anything, they don't work with objects. And so it's easy to define because they just invent nonsense that you're at two places at once, you're in two universes at once, this particle affects that one without anything in between, no mediator, anything. It's all not even magic, because this is just irrationality at its maximum, at the 40th power, like I like to say. It's just nonsense, poppycock. I mean, you're not receiving anything that's worth anything from the mathematical establishment today, because we have the wrong people doing physics. What they're doing really is math, experiments in math, experiments measurement in math, and then they come up with a most irrational theory, explanation, mechanism, causes that they can imagine. What can I say? And you're paying for it. Okay, that's something that should make you stop and think. Okay, so let's get down to our friend today, our uninvited guest. We're going to talk about a fellow by the name of Alexander Belyaev. Belyaev, I think I pronounced that correctly. And he's our uninvited guest. He's from same university as the lady that we talked about the other day, okay? Yvette Fuentes, and it's from Southampton. So I don't have to say much about that again. University of Southampton, it's a state-funded public university. In other words, this is paid for with taxes. And so these people earn big bucks, right, because they have good salaries as teachers, as instructors, whatever, right? They belong to 1 million organizations that are these think tanks. And they get all this money. A lot of it is private also, by the way, but much of it is from the government. So government is paying for this for whatever reasons. That means you're paying for it one way or another. And this is in merry old England, but you're going to see the same thing throughout the world. In Russia, they have this. In China, they have this. In the African nations, and in South America, and so on. This is worldwide. You have the state helping these people out. And what does this fellow do? His name is Alex Belyaev, again, Alexander Belyaev, and he's theory and phenomenology. Oh, Jesus Christ, that must be so scientific. Theory and phenomenology of elementary particle physics and cosmology. Big title there, right? And he does physics beyond the standard model. They abandoned the standard model. It don't work, okay? So they're abandoning it. They want to go into fields. Okay. Supersymmetry and its dark matter links to cosmology. Yeah, these people are looking for dark matter. They cannot explain that phenomenon, the galaxy rotation problem. And so these people think that there's some dark matter out there, which is really dark mass. They call it matter. They're talking about mass. They're saying we have to sprinkle mass on the outside of the galaxy in order to produce the effect that we see of all these stars, of all these galaxies rotating around. And the issue there is that, again, the stars on the outside are traveling at the same speed or faster than the ones on the inside. That's like if Mercury traveled slower than Pluto, right? And you say, how can that be? You would think that Mercury would go around faster than Pluto. And so this is the issue. The issue is that they're looking for dark matter, and they're trying to unite quantum mechanics with general relativity, dark matter belonging to general relativity. And you have all this supersymmetry stuff that they've got, which belongs to the world of the tiny, of the small, okay? And one thing that caught my eye is this guy works on Higgs, little Higgs. Higgless and also the what is called the Higgsino, okay? And that's when I'm interested. You see, there's search for Higgsinos in final states with low momentum lepton track pairs. He published this recently or is about to publish it, one of his last papers, okay? And so what is all that about? What is this Higgsino thing? I didn't see the Higgsino in the standard model. I just saw the Higgs. And yeah, that's why this guy says he's working beyond the standard model, whatever that is, okay? So they're inventing more particles. And you're saying, I mean, are they seeing these things? Or are they going to the lab, the accelerator, you know, and seeing all these particles go there and we're watching all the particles just flow by? Not at all. It's all math, okay? That's the point. It's all math. And it's math that they think they should be inventing because they have no other explanation for what's happening in the lab, you know, at the accelerator. And so what is a Higgsino? Let's start there. And here we have the Higgsinos, superpartner hypothetical particle of the Higgs boson. They work with bosons over there. They're clowns, right? And they say a superpartner. What in the world is that? Well, we'll see that in a second. But it says a Higgsino has spin half, and it refers to a weak isodoublet with hypercharged half. They have all these terms, these beautiful terms that they've invented. Higgsino fields linearly, and by the way, you know, they have no idea what a spin is, okay? They talk about spin as if they knew what they're talking about, and you say, well, spin is like a top. They say, well, no, it's not like that. It's, you know, angular momentum of some kind. We don't know what it is, but they always illustrate it like a top turning. So, you know, they study spin. They don't know what spin is, but they study it and they mathematize it. That's what they do. And it says Higgsino fields linearly mix with gauginos. We have the gauginos and the Higgsinos, okay? Leading to neutralinos, the neutralinos and charginos that refer to physical particles. Okay, so these are physical particles, whatever that is, because particles are vibrations of fields according to them. And so they've invented all these terms, the Higgsino, the gauginos, neutralinos, and charginos. So you better be ready for beyond the standard model, because that's what's coming, okay? The lightest supersymmetric particles, LSP, is a particle physics candidate for dark matter. Okay, that's where they're trying to shoot for. They're saying, we're looking for dark matter. We're going to find it here on Earth. But I don't know how they can do that because, you know, dark matter supposedly weighs tons. It's invisible. It's very small. It's invisibly small. It's translucent. You can see all the stars in the background right through the halo that surrounds our galaxy or any galaxy. And nevertheless, they say, look, it's there. And we're going to look at it. We're going to look for it. We're going to try to discover it here at the accelerator. But it's got to weigh tons. I mean, you know, can you imagine one of these little particles weighing more than an elephant? It says the neutralino LSP, depending on its composition, can be a bino, a wino, or a Higgsino dominated. Okay, Higgsino dominated LSP is often referred as a Higgsino, in spite of the fact that a Higgsino is not a physical state in the true sense. I hope you understood all of that. We had all these enos, okay? We have the Higgsinos, the binos, the charginos, gauginos. No, this is not, this is from the circus, yes, but you shouldn't laugh. This is serious, this is serious stuff, okay? So here we have, just to make sure that you don't confuse them, the little Higgs is not the same thing as a Higgsino. Please, okay, do not confuse them. Little Higgs and Higgsinos are distinct theoretical concepts designed to solve why the Higgs boson is so light, okay? Little Higgs, a particle theory where the Higgs boson is a pseudo-Nambu-Goldstone boson. Okay, I'm glad we have a lot of bozos over there, you know. It is a composite model alternative to supersymmetry, SUSY, okay. Higgsino, the supersymmetric partner, right, superpartner of the Higgs boson, right, is supersymmetric in supersymmetric models. It is a fermion, whereas the little Higgs is a boson, okay. So they have the Higgsino, you got to have, there's a difference between a fermion and boson, okay, and so they're saying the Higgsino, the one they're going to be studying, right, is a fermion. Is it? Or did I get that wrong? Little Higgs models are generally an alternative to SUSY, while Higgsinos are mandatory components of SUSY. Okay, whatever. The point here is that they're inventing all these particles, so-called particles. And they're studying this. You're paying for it, by the way, right? Let's keep that in mind. You're paying these people's salaries. Run it like a company. These people, what are they producing? They're producing names of new particles as we go along. What is this? And you're saying, well, I mean, who's studying the Higgsino and who's studying the little Higgs and all these little bgaedenos and whatever particles? Well, here you have it, okay? This is just the Higgsinos, okay? And if you look it up for this year alone, 2025, you'll find all kinds of papers on the Higgsinos. So yeah, this is big stuff. This is not something out of Hollywood. These people are actually, studying this stuff and spending money on this because, they cost money and big bucks, by the way. Okay, so yeah, forget it. These people are really working on all this stuff and you're paying for it. And they're working and they're just inventing names, the Higgsino, bgaedeno, chargino. What is this? Is this science? Is this what we call science? Where did all this Eno stuff start? Okay, and here it is. It started with this, the neutrino, and Wolfgang Pauli postulated a neutrino in 1930 to explain how beta decay could conserve energy, momentum, and spin. And again, they have no idea what spin is. They barely know what momentum is, okay? And they certainly don't know what energy is. So they don't have any of those words defined. They don't know what they're looking for, but they're going to study them and mathematize them. There's a strict limit on energy of electrons from each type of beta decay, okay? Such a limit is expected if energy conservation is valid, okay? So this is the issue. There was a leftover, essentially. That's what's happened here, okay? And they had to explain that leftover. Experiments prove that a limited and conserved amount of energy is available during beta decay. A new particle was sometimes taking a varying fraction of this limited energy. They had to explain that, leaving the rest for the beta particle. And so this is the new particle that they invented, the neutrino, right? Pauli publicly emphasized that the still undetected neutrino at the time, right, must be an actual particle, okay? So they had an event, something happening, right, in the accelerator or wherever, when they smashed particles, whatever. And when they did the math, they said there's a little energy we cannot account for, or momentum, or spin, or whatever. And so they came up with, and they said, I know, there's a particle there, and it's called a neutrino. And at least Pauli said it is a particle. It's a little ball, right? We're talking about balls, okay? And then they deny it, but that's how they treat it. So effectively, operationally, it's a ball. That's what they're talking about. Then they deny it, okay? And you're saying, well, are they really anybody working on neutrinos, anything like that? This is $100 million experiment that they're doing in Japan. They're expanding it now, so they're spending even more money on it. Okay, they're trying to detect neutrinos, and the way they do it, they go underground. They have this big pool, and it's not really for swimming. I think they put some chemicals in there, and what they do is they want to try to catch one out of gazillions of neutrinos, which are flooding and going right through our bodies, because allegedly they interact weakly or poorly or whatever with matter. So they do not interact with atoms, right? They go right through atoms. Okay, and listen to that. It's a particle that goes through an atom. When I say the same thing for the rope model, they say, oh, Bill, you have two objects going through each other. So do they. They have the neutrinos going right through matter. But with this ocean that they have under the ground, they hope to detect a particle here and there, maybe one in a million years, right? And when they do, I don't know what they're going to do with it, because I guess they're trying to learn what the universe is made out of. And one of the issues is that maybe, just maybe, dark matter could be made of neutrinos. You never thought about that, huh? Okay, so this is what the Japanese are doing. Listen to this fellow, okay?
The T2K experiment uses a vast water-filled cavern buried 1,000 meters underground in central Japan. Everything in this $100 million golden chamber is designed to maximize the chances of catching the precious interactions with matter.
Yes, everybody's paying for this kind of stuff everywhere. They're trying to catch neutrinos. Are there neutrinos? Of course there aren't. There's no such thing as a neutrino, but they've already proved that it exists because they have this leftover stuff. It's a mathematical contraption. And they say we have to explain that, and then we call that lack of explanation, we'll call that a neutrino. And so from neutrino, then later on, they had all these, the bosons. They got married and they had kids. And so it started with this guy, Bozo, and he had the standard model. We were okay there, more or less, I guess, the particle zoo, right? But they went beyond that, and what happened was Bozo got married. He had a wife, okay, and at the circus, okay, so keep that in mind. And then they had all the bozinos. The kids, they had lots of bozinos, and today we have all these bozinos. That's where we're at. So they're inventing all these particles, right? Here you have because they call them super partners. So we have super bozo, right? And he's got all these super partners, right? And you see them there: neutrino, neutralino, Higgsino, chargino. I didn't invent these, by the way. Okay, you might say, Bill, you've invented this stuff. No, this is the stuff these people are researching with your money, okay? By the way, I want you to understand that. They've got all this bgaede, Bino, electroweakinos, singlinos, okay? The only one that's different really is the one at the bottom. It's not called a wino, it's called a wino, okay? And here they're super partners, okay? Because, not only do you invent partners, you have the super partners. That's why it's called a Superman, right? Super bozo, okay? And so this is what they call beyond the standard model. And this is what they're studying. This is what you're paying for, the beyond the standard model. This is the new, they had nothing to do. They had no work. There was nothing, even if you smashed particles, you could not come up with new particles because you needed, according to them, right? You need more energy. You need an accelerator the size of the solar system, or maybe the size of a galaxy, to smash them with enough speed or energy or whatever to create, to find out what they're made out of, right? To find out the next level. And they can't do that. So now they sit at their offices and they do calculations and they say, oh, we saw a new effect. Well, what do we call it? I don't know. Call it Charlie. The other guy said, no, I'll call it Pete. And they have all these names that they're inventing. The Charlino. Okay. So, yeah, the last one is not a wino. It's called a wino. And here it is. Since it's Christmas, there you see it. There's the wino. Okay. I hope you know what I'm talking about. That's the particle of the wino, but not to stay behind. I invented my own particles here. I invented the Higgsino, okay? And I didn't stop there either. So I want my Nobel Prize because for this Christmas, I invented the vodkino, okay? I got them all there, okay? So I hope you have a Merry Christmas. Like I hope to have, and take some Higgsino with you, some vodkino, and some wino. Make sure you pronounce that correctly, okay? And hopefully we'll see you before the end of next year, okay?